Hello and welcome back to At the Symposium. Today we're going to be working on factoring. Now, my last video we did some quadratics, which quadratics and factoring go together. But I realized in that video some people might still be uncomfortable with factoring, so why not just keep going? What we're going to do today, I'm going to show you 3 examples of the most common kind of factoring problems that you'll have to encounter. So if you look at these 3 equations, they look similar. They're all basically quadratics, right? In the kind of quadratic form. But the situation is that the coefficient is different on each one if you take a closer look. So here we just have x2, right? So there's really just a coefficient of 1. Here's a coefficient of 3. And here is a coefficient of 5. So where quadratics get a little bit more complicated is when you have larger numbers in the coefficient, especially larger numbers that can't be divided by the rest of the equation. And I'm going to show you what I mean here. So each one of these is going to involve 3 different kind of steps, 3 different kind of methods. This is going to be the general method. This is going to be a dividing method that we're going to use here. And here is going to be a method called the magic X method. So let's just start with this one first. Remember, when we're doing our quadratics, we're going to start with our parentheses, and we're going to ask the question, what 2 numbers can add up to 10 and also give us positive 24? If you're wondering where these problems are coming from, they're coming from another one of Chris McCullen's books. It's called Algebra. I believe it's called Mastering Skills of Algebra. Blue cover, yellow writing. Great book. We'll be working throughout it throughout the course of these videos. So again, my question is, what adds up to 10, but also multiplies to give us 24? So now again, when you're doing factoring, you got to kind of assume what you can figure out and what you can't. It seems like we can assume this, make a healthy assumption that there's probably some number that multiplies 24 and adds up to 10. Okay? We can start this by just doing our multiples of 10, like doing our multiplication table. So, or not of 10, but of 24. So what goes into 24? Let's say 12 and 2. 12 and 2 go into 24. But if you add 12 and 2, you get 14 and not 10. Okay? So that's not going to work. Let's try another one. What I like to do here is kind of work from the highest numbers all the way down to the lowest numbers. So from there, we can say 12 didn't work, 12 and 2. So let's break this down. Let's break down 6. And let's do 6 and 4. Okay? So 6 and 4 multiplies to give us 24. And 6 and 4 also adds to give us 10. So 6 and 4 looks like our best bet here. So all we're going to do is say x plus 6, x plus 4. If we want to check this, we can, of course, just do our FOIL method and multiply everything all up and add whatever like terms there are, and we should get our answer. But again, when we're doing quadratics, if we want to get our final answer, yes, it is factored, but we're going to set both of these to 0, and we're going to solve the equation, which just basically gives you the same quantity just with the opposite sign, right? So my answer would be x equals -6, x equals -4. It's going to look like this. And that's going to be your answer for number 1. Okay, that's the basic, most simple quadratic kind of equation that we can deal with, the most simple factoring equation that we can deal with. So now let's try and do number 2. Number 2, if you haven't noticed already, has a larger coefficient, okay? And that coefficient is what's going to make this problem a little bit different for us. Not completely, but just a little bit different. So we have 3x squared plus 18x plus 27. Now, what you can do in this occasion, sometimes again, when the first thing we hate to see when we're factoring a problem is when we have a large number of the coefficient. But it's not always a problem, and this is why I wanted to illustrate this, because in this occasion, it's actually pretty simple, because all we have to do, it just so happens that all 3 of these numbers are divisible by 3. So what we can do is just take that coefficient, put it over 3, put this over 3, put this over 3. It just so happens to be the case that that problem works out that way. It doesn't have to be the number 3, it could be the number 2, whatever situation in which your leading coefficient is also divisible by all the rest of the numbers in the equation, you can do this. So now we're just going to have x squared. 18 divided by 3 is going to give us 6x. Now 27 divided by 3 is going to give us 9. So now we have x squared plus 6x plus 9 is going to be our quadratic. And then we just do just like we did over there. Pretty simple. Now we just have to ask the question, what multiplies to give us 9 and will also add up to 6? Pretty simple. I think we could do that one in our heads, because 9 can be only multiplied by 2 numbers, and that's 3. So 3 times 3 is 9, and 3 plus 3 is 6. So we're going to do x plus 3, x plus 3. If we drop that down, that's going to give us x is equal to negative 3, x is equal to negative 3, and our answer is going to look like this. Okay, now for the third one. Here's the one that's going to be the most involved, but you're going to learn a special technique here that's actually really going to help us. So again, the problem with this one, what's the problem with this one? Well, if we take a closer look, we have a leading coefficient, but not like in the last problem. None of this is divisible by 5. We can divide 5 by 5 and get rid of the 5, but we can't divide 37 by 5 or 14 by 5. So we're out of luck. We can't use that method. So what do we do when we have that kind of issue? We do something called a magic X, okay? And the magic X is just a way to kind of lay out the problem when you're doing it, or lay out the method. So the magic X, remember when we have a quadratic, we have A, B, and C. So what the magic X is going to do is we're going to take our A and C variable. We're going to take these numbers, which in this case, so A and C equal 5 and 14. We're going to multiply 5 and 14. And we're going to see what answer that gives us. If we multiply 5 and 14, it should give us 70. And we're going to put B down here as 37. Okay? Now what we do, what this basically does, multiplying A and C gives us a new number to solve for, where we can ask the same question as we always ask when we're factoring, which is, what number goes into 70 that will add up to 37, okay? So we've multiplied A and C to give us a new number to ask the same sort of question. So instead of asking what number goes into 14, that would give us 37, because 14 is too small to give us any number that would add up to 37. So we have to go higher. So we multiply A and C, and that gives us a larger number. Now we can ask the question, what do we multiply 70 by to give us 37? So what do we do now? We just make some room on this board. What do we do now? Well, we ask the question again. What does 70 go into? That can also equal 37. So we can do this, write our little tree again. Again, I like to start with the highest thing, so we can just think of 70, or 10 times 7 is going to give us 70. But if we add 10 and 7, it only gives us 17. So that's not good. That's not going to work. We know that we're going to have a pretty high number to be able to do this, because we're trying to add up a number that adds up to 37. So 17, that's way off. What else do we want to try? Let's see if we get 5 and 14. 5 and 14 would give us 70, but then what if we add it up, it only gives us 19. So that's not going to work. Let's see if we divided 70. Let's see if 70 goes into 2. So 2 goes into 7 how many times? It'll go into it 3 times. That'll be 6. You're left with a 1. And so 10. So that's 35. So 2 goes into 70 35 times. Okay. So let's say 2 and 35. That gives us 70. And if we add 2 and 35, we get 37. So that's going to be our answer. So what we're going to do here, since we found the answer, we can put, this is why you do the magic X thing, because you put your numbers on each side. So now we have 2 and 35, okay? And we're not done yet. We figured that out, and that's good. But now we have to figure out how to position all this into our answer, which is going to take place in the 2 parentheses. So what we're going to do is we're actually going to put our answer, both answers, over the leading coefficient, which is 5 and 5. Now, remember that we have to reduce our fractions. So these are basically fractions. We put our answer over the leading coefficient, okay, on both sides. That's where the 5 comes from. But now you have to reduce our fractions. Does 2 go into 5? 2 doesn't go into 5, so we're going to leave that there. So that's going to be that. Here we have 35 and 5. Does 35 go into 5? It does. 35 will go into 5 7 times. So we're going to have 7 over 1. Okay. So 35 over 5 equals, it really equals 7. We're going to leave it over 1. There's a reason why we're going to leave it over 1. We're leaving it over 1 because we want to reinstill in ourselves that we have a leading coefficient. Our coefficient doesn't go away. This is the whole point about putting them into fractions. Okay, so we have our answers. We've reduced them as much as possible. So we have 2 over 5 and 7 over 1. Since we've reduced the fraction, we got 7 over 1. Now we just have to figure out how to place this into our answer. So all we do is take the coefficients. Remember, the bottom number, the denominator is always the coefficient. That's where we got 5 from. So this is our coefficient. So that means this is going to go here. And that 1 that we have here is going to go over there. That 1 that we have over here is going to go there. Same one. Just showing you for illustration purposes. So we have 5x. Again, that coefficient goes there. And then whatever we had on the numerator side, which was 2, we'll make our constant. Okay? And then here we had 7 over 1. So that just means an x, which we could have just intuitively figured out, but I just want to illustrate it, right? So our 1, it means we have an x there, and plus 7 for our constant, okay? So let me just reiterate this again, just a little bit so we understand. We took our magic x, we took A and C, which was 5 and 14, gave us 70. We put B on the bottom of the x. We asked the question, what number multiplies by 70 to give us the number 70, but also adds to give us 35? And we figured out that answer was 2 and 35. If we multiply 2 and 35, we get 70. If we add 2 and 35, it gives us 37. Then we took this and put our coefficient, our leading coefficient, on the denominator, made them into fractions, and then sought to see if we could reduce those fractions. If we couldn't, we just leave the answer like that. If we can, we just simplify the fraction. So 30 over 5 really becomes 7 over 1, and we keep it over 1 because we want to see the coefficient. And we take the coefficient here, we move it there. We take this coefficient here, we move it there, and then the numerator just becomes our constants. And again, if we FOIL that, then that'll give us our answer again, and we can check it. So if we did all that, the math, and multiplied everything, we should get 5x squared plus 37 plus 14. So those are the 3 most common factoring problems you're going to run into, and that's how you deal with them. The first one, very basic, straightforward, just factoring. The second one that we did, if it's divisible, always check to see if your problem is divisible. The reason why you want to know this is because sometimes you might see a problem like number 3 up here that just has a large coefficient, and you think, oh, well, I just have to do the magic x method, which is a little bit more complicated and drawn out kind of method. You'll save yourself some time if you first look at the equation and ask yourself, are all these numbers divisible by the coefficient, the leading coefficient? If all the numbers are divisible by the leading coefficient, you'll save yourself entirely from doing the magic x. The magic x only has to happen in a situation in which you can't divide all the numbers by the leading coefficient, in which case we just do it like we did there, and we have our answer.